we find the stream. Oh, I'm going to start without my data. Did I not open Chrome?
I think you just judged it.
That does sound like what I would do. Okay. I think I'm going to use a combination of teaching techniques, none of which are particularly appealing, but all of which will work. And I don't know how I feel about that, but that's what we're going to do. So I'm going to teach a little bit off of this device and a little bit off of this device. And the combination of those two devices are going to accomplish all of the goals I have. We'll submit a ticket to IT, and then we will do the same thing next week for 14 consecutive weeks. And then right at the end of the semester, they'll fix it right after the last day of class, right? Okay, yeah, we're familiar with how things work. I actually didn't know that my Bing rank was this high. I wasn't optimizing for it. Some of you use Canvas, right? Can I hear it for Canvas? Yeah, Canvas. I don't use Canvas because Canvas is maintained by the same people that maintain these projectors, right? And so when the school website went down last year, all my stuff stayed up. And then at the end of every year, I get course evaluations, and exactly half of them say, thanks for not using Canvas, and the other half say, why can't you just use Canvas? Anyways, for my party trick, my first party trick is I will type my first and last name into a search bar and see that I am the first result. And for the next trick, I will type my first name and my university affiliation into the search bar. I would argue that this is as easy to find as a Canvas website. You don't have to agree, but I have put a lot of work into getting my page ranked this high for you because I care about you and want you to succeed. That projector is shining right in my face. Why can't that one be the one that works? Okay. If we click on this link, I understand there's a lot of stuff here, but you are students. Therefore, you are interested in being taught, I think. I think that's the understanding. I'm teaching somewhere between 2 and 4 classes this year, depending on the classification. And you are in my cybersecurity cryptography class. This is the Bitcoin Genesis block. It'll be a recurring character this term. This is the course website. Okay. Back. This is the course website. I always apologize to my students. I try really hard every semester to find a topic that isn't 6 characters in length, and I've just never found one. So unfortunately, every single lecture and sub-lecture will have a 6-character title, and we'll begin today with Podman. I have this website set up so that I'm not screen capturing this screen. That's okay. I have this website set up so it brings you to the schedule by default, because this is where I expect you to want to be most of the time, except for in one special case, which is the first time you visit the website, which might be right now. The first time you visit the website, you probably want to learn about the course in particular. This is the page for this course. There's not too much on here. The only thing that's relevant is on the syllabus, and I want to show you a few things on the syllabus before we get any further. This is still being edited because there's something I want to ask you about. I think the way that it makes the most sense to conduct this class is to do 90-minute lectures, followed by 90-minute lab sessions where you're allowed to eat, followed by you going home at 9 o'clock and watching a 1-hour-long video that I've made in advance. And the reason I arrived on that is at a few points of time in my life, I've attempted to teach technical content from 9 to 10 on a Thursday, and I have not solved that problem. Now, it could be the case that you're like, no, we're totally cool, we want to keep working on lab at 9 or something. You just have to let me know if that's what you want to do, right? So my proposal is, I have the bonus lectures recorded for the first couple weeks. You can go watch them whenever you want. I was counting that as your 4th hour. I'm not going to cut more than 1 hour, right? And then in addition to that, giving you a lab that you can work on or not while you're eating. That to me added up to a better outcome than trying to learn about pointers and recursion at 9:45 p.m., which seemed impossible. So that's what this means. That is fewer hours than normal. This is fine for credit hour compliance. It might not be fine for like your learning style. So that's why I have to talk to you about it. So we'll try that out this week and next week, and then we'll evaluate in week 3 if that's the direction we want to stay going. There are 2 optional texts for this course, and neither of them follow the course, but all of them address the content of the course. This course is an n-dimensional course where I'm using application domains to teach underlying technologies, which means I'm using the technology of the C programming language to teach cybersecurity. This is atypical. This was motivated by teaching a sort of less technical or high-level cybersecurity class for a few years and spending an enormous number of minutes trying to explain what buffer overflow was to students that didn't know what a buffer was. And I was like, why don't I just teach buffers, like an independently valuable thing to know, and then separately also teach about buffer overflow, right? So that's what I've arrived at as a solution. This isn't experimental. We're deploying it for the first time this year. It should work. This is the instructional text for the C programming language. I do not know that this is a legal copy, but it's hosted on UCSD, and I'm assuming that means it is, and I don't want to know. So if you find out, don't tell me.
If it was DMCA, you would take it down, right?
That's, I believe you. Thank you. All right. This one is definitely free and open source. This is the graduate course in applied cryptography at Stanford. They update this book every semester. So I even suspect it was actually updated this January. We just don't know yet. I'm not going to be following these texts. You should follow them if you like textbooks, right? I'm sort of a grade atheist, and that got me in trouble once when there was a student that got the lowest grade I've ever seen on a midterm and also turned in no homeworks. And I had to give that student not an A. So that's how you can get not an A. So just don't do either of those 2 things. The reason to use, we can call them lax, or we can call them like student-centered learning policies. I think the stuff I'm teaching is like kind of a little hard. Like, I wouldn't necessarily expect like a normal person to get all of it correct on the first try. And I think if I had to grade the way that like a 100-level calculus class is graded, we would just all get Fs, like including me. And so one of the ways you can solve that problem is like, oh, I can teach stuff that's like comically, hilariously easy and also boring. Or I can just teach the coolest stuff in the universe, and like if we don't get all of the code to run every time, be like, eh. So that's what I've arrived at. And if it doesn't work, we'll change that as well, right? It is quite easy to make this stuff comically, hilariously easy. There's this language called Python, and you just do things in that. And then it's impossible to make. I've never seen a bug in Python code. They don't exist. A corollary of the like grades being made up thing is, I don't know how many of you have like ever taught a class like as a TA or something, but students' favorite thing to do is ask if they can turn in homework late. And I don't know what motivates this, so like if you do it, you know why. And the thing I always say to students is, well, the due dates of the homework are not actually related to like seeing like what a good person you are or like your moral value as a human being. They're actually related to when you should stop working on that homework and start working on the next one because course instruction has moved on. So if you are still working on a homework assignment that is overdue, you should stop doing that and start working on the new most recent homework assignment. It is possible you should even do this before homework assignments are due. You should just cut your losses and move on. It has not been my experience that it is commonly the case where students that like turn in something 6 days late, like learned anything, right? Usually whatever problems are contributing to that being late, which is usually not related to class. It's like, oh, my car broke down. It's like, well, yeah, okay, so then you should not do this homework assignment, you should do the next one. I think different faculty members have different AI policies. I suspect that last term you had some classes you couldn't use AI and some you could. Does that sound right? Something like that? Okay. It's bugging me that's not zoomed in. Do you all know who Linus Torvalds is? He wrote Linux. He said you can use LLMs to write code for the Linux kernel. And I think, like, having never written the Linux kernel, because only one person ever has, presumably that person like knows more than me about this stuff, and I found that pretty persuasive. I'm going to start going through slides here in a minute, and the slides are going to be like, this technology we're going to use this term was developed to write the Linux kernel. This technology we use this term was developed to write the Linux kernel. I'm going to do that 3 times. The technologies to develop the Linux kernel are appropriate technologies for cybersecurity research. They're appropriate technologies for master's level computer science education. Therefore, I am saying you're allowed to use AI in this class. Please do not cite my AI policy to use AI in other people's classes if they tell you not to use it. That is the thing that I care about. And I think that's the only thing on here. I don't know what time commitment you were all told. Under the Carnegie Hour classification, for this class with 4 credit hours and 14 instructional weeks, I'm entitled to 9 to 12 of your hours outside of class. That seems like impossible by construction, but I have written homework assignments that are intended to take that long. There's 2 ways to handle this. One way is to not finish them, and then the other way is to work together. And I'm recommending you work together, but I don't know if that's feasible given your work schedules. Since this is an experimental class, we'll be taking a measurement after 7 weeks via a midterm, and at that time we'll be able to assess the level of course difficulty and appropriateness of the time commitment expectations. That said, if you do not work on this stuff outside of class, I think you should change classes. I think you would get very little out of this class if you don't like hack a little bit on your own. I could be wrong. You're certainly allowed to like just come here, not do any homework and see what happens, right? Like that won't offend me, but that seems like an odd design decision. I think that's everything. Cool, yeah. Any questions? We'll go over class more so you know what to expect. Nice. You got this email from me? Please be live. Oh, maybe it's not. Does anyone know how YouTube works? Am I streaming? I thought I was streaming over here. Is it private? Oh, it's unlisted. That's annoying. I have a plan. I didn't have it on purpose, right? I'm going to stop it and start again. Let's see.
I don't remember.
I don't know how long it'll take to show up. Cool. Is that resolution okay? Yeah, it looks fine. How long's the lag? Oh, that's really slow. I alt-tabbed over here and that hasn't changed yet. All right, well, okay. I don't know why I thought I could click through that. I might have to use Zoom. I don't want to use Zoom. I don't, okay. This is the playlist. So the tonight's class is similar to a Portland or a Salem lecture that is also recorded. The 90-minute labs I'm not recording because I'm just walking around to the room. My plan was to, the reason I was wrestling with this for so long, my plan was to physically do the lab in front of you, which I did not do in Salem. That looks infeasible with our technology setup right now. So I will walk around and talk to all of you, and if it's resolved ever, then I will start live coding. It is, in fact, possible for me to do this via Google Cloud Console, and I'm not sure that's better than not watching me doing it, right? Anyways, here are these. This is the bonus lecture for this week. X8664 is for next week. Primes is actually going to be a canceled guest lecture. We have a guest speaker that week. So you can still watch it, but it's not actually part of the course content anymore. I'm going to mute that. Okay. This is the website we're currently on. These are the textbooks I've already shown you. And here's some cheat sheets and downloads. I think there's also a Discord. And some of you are in there, and you might have noticed that the undergraduates yap a lot.
Yes, I do.
Yeah, I'm sorry about that. I told
an adults table channel.
Yeah, so I was thinking about giving you like access to that Discord and separately making a different Discord, or I can give you a tag and give you your own channel.
I think the channel.
You like channel?
We can just mute the undergrads.
Okay.
And you don't have to make the announcements twice.
Yeah, okay. So that's good for me. I'm starting to open Discord on here. We'll just set that up tonight. And the way we'll do that is I will verify you are an adult by asking you your Discord name in here. And we'll just sort it out in person because that's the easiest way to authenticate. So, yeah, there's some of them that they really like talking. And I understand that because I like talking, right? So I set a bad example for them. Okay. It's 6:24. Okay, I'm fine. The weeks are 0 indexed and they're in hexadecimal. Like, I can't help who I am, right? I'm teaching in our class this term, and it's week 1 in that class, okay? It's not OX1. It's not OX0, it's just 1. I can do it if I want to, right? But in this class, I'm entitled to use really obnoxious numbering schemes, right? So I'm going to do it. Welcome to class. Do you all have a GitHub account? Okay. The first homework is ready. What I have learned from talking to people that have started working on the homework is that I selected the first homework as something that you don't have to use any language features in. So you don't have to use arrays, you don't really have to use any string methods, you don't have to use print or get, well, you have to print, but you don't have to do file IO. The only thing you do is you get a command line argument the exact same way you get command line arguments in Python. And then you print something out the exact same way you print things in Python with a format print. So it does specifically have to be a format print in C. And I was like, this will be no problem. And someone got their code to do a bus error by doing a failed memory allocation. And I was like, I don't know why you're allocating memory to change one character into another character, which is like the assignment is, right? So I'm going to motivate Amigna a little bit more. In my computer, this W is represented by 8 bits. Those are ASCII bits, 7 of them, and then the 8th one is a UTF-8 bit, which is set to 0. That thing is the same thing as a number. What the Enigma machine does is it takes a subset of 26 of the possible 255 values that could have and changes it to another subset of those 26 of those 255 values that happens to represent a different letter. For example, this E. Astute observers will note I have only selected capital letters. It only works on capital letters. You can design it to work on lowercase letters as an extension if you want. I won't stop you. I won't even know you did it. I'll just press the autograder and be like, wow, it worked. And you'll feel like a sense of self-accomplishment, or you'll like come and you'll be like, hey, Calvin, look at this cool code I did. And I'll be like, that looks like cool code. Good job. And that'll be all you'll get out of it, right? If you feel like, wow, I don't know how to use dictionaries in this language, that should be a hint, not that you should figure out how to use dictionaries in C, but that a high-level language trained you to not know how to write code. And so I didn't realize this until I gave the assignment, but I do think there is a bias in like Python programmers, which many of us are, or JavaScript programmers, to be like, ooh, this thing seems hard, I should go find a language feature that solves the problem for me, instead of, this thing seems hard, am I doing it in a way that's deliberately difficult? I didn't realize this, but a learning objective of this course is to stop doing that. Right. So I'm not changing Enigma because a bunch of people thought they needed arrays for it. I'm telling you, don't use arrays on Enigma. I don't know why you would need them. I've put my function archetypes in the Discord, and some of you can see it. It does not matter if you complete Enigma or not. I'm curious to see how far you get. I'm in Edge, aren't I? When I moused over something, I saw Copilot. Look at that. Why would I ask Copilot now? That prompt does not make sense. Do you all know what the Enigma machine is? Do you care?
Sure.
Yeah, okay. All right. So there's this, the bad guys, the Nazis, right? They were like doing bad guy stuff, and they were doing it in the light of day, and so they didn't want other people. And in this case, the British Empire are also the bad guys, so I'm going to have to be careful about how I refer to them. So there were slightly less bad guys that were trying to figure out what the first bad guys were doing, right? And so the Germans were encrypting messages via a machine that had 3 rotors in it. And the way a rotor works is you press a key on a keyboard, that key sends a charge through a wire, that wire changes a letter to another letter, and then the wire comes out. And if you do this through a rotor forward and then backwards back through the rotors, it is encrypted 7 times. And that is very, very difficult to brute force in 1939 and very, very easy to brute force in 2025. When I couldn't figure out how Enigma worked, I just wrote a script that cracked it, and it took like 15 minutes. So this thing is not that secure anymore, right? And it was really, really hard to crack the first time I cracked it. So there's this fellow named Alan Turing who went to school in the United States and then went back to Britain, who, like, the way I explain this, because this is how I understood Enigma, Turing was raised by parents to not necessarily think of numbers as in base 10, which you might find extremely relevant when you're working on the Enigma machine. Because I really felt like I was working with base 26 numbers. You may not feel that way, but I really strongly felt that way, and it was very easy when I was working with base 26 numbers, right? So my impression is Turing looked at these things and was like, hey, these are base 26 numbers, made a little gadget called the bomb, which has like an E at the end, decryptor, and like did something that helped the British Empire win the Second World War. And I'm not a historian, but that's the story. Anyways, Turing did this 3 years after inventing the Turing machine, which is the model of computation we still use today, right? So interesting historical figure. This is what it looks like. This is a rotor, these 2 levels, right? So it takes the input E and directs it to the output J. Then there's a wire from this output J to the input J on the next rotor. So these things are a rotor. I need this page again. Oh, the bonus content for this week will be helpful with this, but it is up to you how helpful it is. It may be easier to visualize the rotors and text in this manner. There is one wrinkle in Enigma that makes it non-trivial, because otherwise you're just applying functions directly. These things are called rotors because they rotate, which means you can take an E, rotate it forward through the alphabet to become an H, direct that H through the rotor, get a P, and rotate that back to an M. And we'll notice that this is distinct from the E to J transition we would have otherwise had, right? So this rotating is non-trivial. It took me a long time to figure out this is what it meant by rotating. So this is I'm going to scroll down a little bit, then I'm going to call on you. This is one round of the Enigma machine. There are 7 that go fast, medium, slow, reflect, slow, medium, fast, symmetrically. And each one of these is a simple character substitution. Yeah, but.
You said P rotated back to N, like that made sense.
Right, okay, so I don't know that it made sense. P is a letter in the alphabet. It has some position, and I think its position is 15, but I don't know. So when I go backwards through the alphabet from P, I have a decrementing position or index within the alphabet. this corresponds to the exact same forward displacement as present up here. So when E rotates forward, I find the index of E, I increase that index by some value, and I get a corresponding character in the alphabet, which is H. I can reverse that process by taking P, converting it to an index, subtracting 4, and then converting that back to a letter.
So the rotors are in alphabetical order.
The rotations are in alphabetical order. The rotors have no order. They are expressed using a block cipher, which is this mapping. Okay. I don't know that Enigma makes sense, but it's fun. Here's what it looked like, and you can see an example maybe of like how it works, which is like when I press this A, R highlights. You can validate yours against these examples. And this example here, you can see the internal rotors, and so when I press A, we light up Z because we go forward through one rotor, forward through another rotor, forward through a third rotor, flip through a reflector, and then go back through. If this makes more sense to you, think of it this way. But this transition between letters, so there is an A to Z transition right here. That's what represents the top to bottom. I found that easier to express with this notation here. So there's different ways to do this. There is also separately a Python implementation that you can review as well, which may or may not make sense to you. When you look at Python that looks like this, is this understandable in some way? It's a lambda expression with list comprehensions, which is the only way I write code. But you can always either manually change this into the def format with for loops, or you can ask ChatGPT to do it for you. That's fine. I guess I didn't ask a generative AI if they could write this, but I'd assume they could. It might be worth asking. Okay. That's Enigma. Give it a shot. The reason I was so interested in assigning Enigma as a C programming language is in Python, if you're trying to turn one letter into another letter based on its position in the alphabet, you're probably either going to be using a string and querying it for indices, or you're going to be converting the letters into their ASCII character codes and back. And both of those felt really awful to me. In the C programming language, and one of the core learning outcome, much more important than getting super familiar with ciphers. In the C programming language, a letter is just a way of printing out a numerical value. There is not a separate type for letter versus there is a type for value from 0 to 255. What this means is you can do things like use a letter as an index in a list or an array. I was very frustrated implementing Enigma in Python because I couldn't use the letters the way I wanted to. And if we look back, do I have it open here? I'm changing, I don't remember which way char and ord go, but I think this is a character that I'm turning into a number, subtracting a number, and then looking up what the index of that number is in the alphabet all at once. And in C, that is a subtraction. And getting to experience how a low-level programming language stores information is a good way to begin thinking about the ultimate objectives of this class, which is that when we see bits in a computer, we should understand they are just bits and that we give them meaning with the code we write. They don't have an inherent meaning. That means they can't be used in certain ways. So I hate this because I thought it made my code harder to use. And I changed languages and the problem went away. Okay. We'll motivate that all by introducing the course. What time is it? It is 6:36. Okay, that's not that bad. There are 4 enabling technologies that I would like to introduce today. We will get to them. If you are on Windows and you finished running this command, what you should be able to do is run this command and get access to a Linux command line. which I will demonstrate on this machine, and then I will show it to you in a minute. Oh, I've completely tanked the performance of this machine. If someone's computer is wheezing over there, mine wants to be doing that. It just doesn't have a good enough fan. Is this hot? Oh yeah, I'm quite hot. When we type in WSL, you get a Linux command line. If you are on Mac, you already have access to a Unix command line, and if you are on Linux, you are on your own. If you already use Linux for fun, I don't know why you're asking me for half the things, right? So, if you are in that situation, it might be a good idea. Oh no, I lost my Podman. Okay. You can go ahead and use your package manager to install Podman, Vim, GCC, and Git. You probably have Git already. You probably don't have the other ones. Are you all taking Data 503? I think in that class you use Docker, which is the version of Podman everyone except me uses. The reason I stopped using Docker is because I taught cloud computing last semester, and in the middle of that semester, Docker Hub turned on rate limiting on all of their container registries. And if those words don't mean anything to you, that's fine. But they ruined my class, and I hate them. So I'm using Podman out of pure spite. Then I found out Podman is from Durham, North Carolina, which is where I went to school. And so that's just two good things, right? So go ahead and install either Podman or Docker. I'm going to say Podman this term. You can use Docker if you want. You can probably also use Podman in the Docker class if you want. I don't know. Could be fun. I'm strongly encouraging you to use Vim instead of VS Code or whatever code editor you use. GCC is quasi-mandatory. There is a drop-in replacement for GCC, just like Podman. You can use Clang. I'm going to use GCC this term. It is not a political choice. I just had to pick one of them. And then Git, we are probably familiar with, and I would like us to start using it more at the command line this term. I, for years and years and years, believed that everything you could do in Git was easier to do at the command line. And then I tried to mass change the visibility of a large number of repositories. And the way you do that at the command line is you manually type in a JSON object into an API. But I did it. So you can do everything at the command line if you want. Okay. So the way to do that is you would come over here, you would type WSL, as I've demonstrated many times, and then you would probably type sudo apt podman. I think that won't work, so I think you have to type sudo apt update and sudo apt upgrade. And you can work on those things in the background while I lecture, and when I walk around, I'll help you with all of them, and I'll have a video of them on this screen if I can get my computer to work. Or, I mean, my computer's working fine. It's the display tech that's not working, which is fine. Okay. Okay. My name is Calvin Deutschbein. My last name has 5 consecutive consonants, which means it is unpronounceable. Fun fact, if you only look at consonants and vowels, it is a palindrome. It is 1 consonant, 2 vowels, 5 consonants, 2 vowels, 1 consonant. And so that's how I remember what my name is. I tend to go by Professor Calvin. Undergraduates are more reluctant to refer to people by their first name, so I'm probably expecting to get Calvin from you, but that's okay. You can do whatever you want. I use they, them pronouns. I am trapped, just like all of you, in this mortal coil, and I have an office in Salem, which benefits you not at all. I don't remember, so I wrote 10 a.m. to 2 a.m., and I actually have to sit down and figure out if that's when I'm awake or asleep. But I leave class a little bit after 10, and then I check email, and then at some point I go to bed, so that's 2 a.m. And then I wake up the next day at 10 a.m. And the thing is, I have a meeting tomorrow at 8 a.m., and I'm not sure who's going to go to that meeting, because I will be asleep. So the best time to find me is from 10 a.m. to 2 a.m. on Discord. I can meet you in person. Now, you here on the Portland campus have the great benefit that I do live up here. So if you want to meet me for coffee during the day, especially on a Wednesday or Thursday, Wednesday or Friday, those are the days I'm up here, we can set something up, but I'm not going to hang out there for 6 hours every day. So just let me know. I am also on Twitch, Instagram, Blue Sky, and also I have been grinding out the analytics on LinkedIn lately. I've been just cranking LinkedIn posts. So if you follow me on LinkedIn, like, comment, subscribe, right? Maybe share it with your followers. My doctoral thesis is on something that is actually much more similar to the content of this course than any other courses I've gotten to teach, which is very exciting to me, because talking about things you know about is more fun than talking about things you don't know about. I mined the secure behavior of hardware designs. A hardware design is the piece of code written in a hardware design language by a hardware engineer at Intel Corporation or one of their competitors, which describes how a photolithography machine prints a semiconductor device to operate as the Intel Core i7 inside of this device. There's just a lot of cool stuff that go on in that process. Turns out the people that write these hardware design languages, much like us, are humans and therefore write bugs. And sometimes those bugs make it into mass production and are printed onto millions or even billions of chips. And when that happens, people refer to that as bad. And so my doctoral thesis was about trying to prevent that from happening. And we got some of them and not others, and we get better every year. That's more a curiosity than anything else, but it should motivate two things. I am interested in security, and I am interested in low-level details, and that's what this course is on. Over the course of my career as an educator, which is relatively short, this is my 8th semester teaching as a professor. I taught a couple semesters before I became a tenure track professor, which is sort of the full-time version. I am pretty sure there's only two things you have to know, which are pointers and recursion. I have suggested that maybe the third thing is how to write proofs. I want to point out that a lot of the stuff I do for fun, like code golf or telling the difference between programming languages, I don't know that that's super useful. I think it's fun. Everything in the universe, as far as I can tell, runs on pointers and recursion. Pointers is the difference between when I have a number in my computer that is just some bits, if those bits are referring to a numerical value that I care about the numerical value of, like the number of times I've gone through a loop, or if those refer to the address of something I care about. For example, they refer to how far through an array I have gone in my various loops, right? This is logically identical to, I think, the relatively entry-level computer science conception of key-value pairs that are often used in dictionaries and hash tables. Pointers are just key-value pairs, but they are key-value pairs where the key's end values are numerical values expressed in bits inside a physical computing device, and that can make them harder to think about because there's not as much attached meaning. I think one of the nice things about a dictionary is if you Google dictionary, that's actually a word in English. And if I go out on the street and ask someone what a dictionary is, they'll say, oh, that's something that relates words to meanings. And if I ask someone what a key-value pair is, no one has any idea, right? So there is this escalation in difficulty that occurs when we start thinking about pointers, but it is the same conceptual idea as other computer science concepts. Do you all know what recursion is? Okay. I wrote a recursive exponentiation function here. Recursion is cool. It is mostly cool when it's applied to things that would otherwise be very annoying. Here is a coding example. I'm going to try and get coding to run on this device right now. And I bet this will work. What do you think the Pyodide command line is? If I click here, it's not just going to show it, right? I want to, let's see. Oh, there we go. Okay. Okay, we have Python working thanks to some hardworking web developers. Or here I'm going to do a demonstration. Based on the difference between keys and values and the difference between pointers and anything else. So in the Python language, we have integers. We can see the type of a variable that contains an integer. We can see that it is a class integer. We can take the ID of an integer, and we can see that it does have, and that is a physical, it's a virtual location in physical program memory, right? So we think of it as corresponding to a specific, actually existing semiconductor. In practice, maybe this is true or not true. It is probably less true because I'm running in a browser than it would be otherwise. You know, between friends, we cannot be too up in arms about that. There's some interesting Python features, which is that all ones have the same location. And I think twos have locations that are pretty close to ones, which is kind of interesting, right? Also, we can note that 84 and 68 are some distance apart from each other. Do they happen to be 16 apart? Which also tells us then that the integer types in Python are of size 16 in some way, right? And if we aren't sure about that, we can test our work. And in fact, 84 plus 16 is 100, right? So there are emergent phenomenons from low-level programming languages that begin to appear in Python. There's one example that I always try to, or there's two examples I'm going to show you in Python why I am unconvinced that this language is suitable for cryptography, and they're the fact that math doesn't work in Python. And so let me show you one example. I was teaching applied machine learning on Monday, and we had a data set where the average was 69.3. Are many of you in Data 505 with Hendrik Oram? So this is the average height or median height, I don't remember, of either men or males in some self-reported data set, right? And we were talking, and we said, hey, is 69.3, how tall is that the way humans usually say it, which is some number of feet and some number of inches? Well, you can take the integer division of 69.3 by 12, and then you can take the remainder, and I cannot talk and type at the same time because I do not have parallel processing in my brain. I think I take that mod 12. And I would have thought that a computer, which are supposed to be pretty good at things, would note that this number is not 60 less than that number. In fact, it has the wrong number of digits by quite a bit. Now you might say, Calvin, aren't you being a little bit hard on the computer over that number of zeros 3? It's like, yes, but also, like, is this not objectively wrong and also a very, very easy calculation to get correct, right? So, like, if I gave this to a 7th grader, the 7th grader would get this correct at higher probability than Python, right? That's a bit annoying to me. I think you probably know what this does, which is that is 10 to the 100th power. That is a Google. And it is probably no surprise to you that that is equal to itself and not equal to itself minus 1. Right? That's unsurprising. I got a little bit annoyed when I found out that these two values are equal to each other, because I was pretty sure they were different because I just checked that. So anyways, we're going to do our cryptography in the C programming language. So I'm not going to apologize for that. Let's take x and we'll set it equal to 1. I'm going to just write this code that I have over here. I'm going to write a little function. It's going to be called addx. Yes.
Can you explain why is that next part true? The second group?
This one?
Yeah.
There's extreme rounding when we use non-integers. The integer data type in Python is infinite precision, and it just slows down. One way to tell this, let's see. So I think I can run that, and like it's crashed, it's gone, right? But I think if you do this and you put zeros at the end, it'll just say overload. You can check. Fidi's probably going to be pretty mad at me. Like, I just tried to do numerical computing inside a web browser. Yeah, I figured it's not responding. No. That'll be fine. Okay. I don't know what'll happen if I do this. Can I do that? That's fine. I did 56 right at it. Yeah, so it just says, oh, we overloaded. Yeah. That can be nice, right? Sometimes you do just want an overflow. Sometimes you really need to know what that number is to unencrypt something, right? RSA, which is the famous public key algorithm, they need 496-digit numbers. Python's like not super good with those, right? It's a little bit slow. It is in fact much easier to work with those numbers in Python than in C, but you will not understand, I don't think, how much nicer it is until I force you to try and do it in C and you hate it. So we will do that later on. So there's a bit of rounding here. Thank you for the question. And back to pointers. So this x is probably going to have the same value as last time. We're working with the same virtual locations. I write a function that I'm going to call add x. It glitched a little bit, but it's okay. See how I'm supposed to have 3 dots there for sure, right? Is plus equal defined in Python? That's legal in Python, right? Python programmers, okay. I think, oh yeah, it doesn't have plus plus, and I don't know that's a different operation. Yeah, okay. So we have x. We add x. Now that just doesn't work, right? Unbound local error, blah, blah, blah. Well, that makes sense, right? I defined x outside of the scope of the function. It's unclear why the function would know what it's talking about, right? So I'm sure that means that if I put a 1 inside a list, the same thing will happen, right? That's what would happen in what I like to say a good programming language, you know? Wait a minute. That's supposed to cause an unbound local error. And in fact, it doesn't. It actually just increments the value. Why is that? Well, this x has some ID, and it's pretty different than the ID of 1. And it's also different from the ID of other lists that contain 10, whereas every one has the same ID. In Python, numbers, especially small numbers, are implemented as values. There's just some number of bits there, and they're set to some fixed value. Lists are not. Lists are implemented as a location, and whatever is present at that location is what's worked on. What this means is that a function that works on a location behaves differently than a function that works on a value. One of the things I don't love about Python, in addition to it not being able to do arithmetic, is it makes it non-obvious which one of these things are going to happen when you work with anything. For example, right now, having just told you this, what is it going to do on tuples? I don't know. And in fact, tuples are immutable, so we can't even check the same way, right? We would have to find some other way of inspecting it. I don't love that those have different locations in program memory, but they have wildly different locations in program memory, right? What is going on here under the hood is pointers. This is pointers. It is the thing called pointers. That's one term we use for them. And so I'm arguing in this class, when we're trying to be precise and successfully encrypt and decrypt things and not make numerical mistakes, it is hard to use Python because it does stuff like this under the hood all the time. In exchange for doing those things, it has a lot of niceties, right? I think many of us like using Python lists, and many of us probably really like using NumPy arrays, right? And that's all well and good. But in fact, there are things that just don't work. Does the format of this slide seem at all strangely familiar to you? Very good. So this is a ChatGPT formatted slide. One of the things I always notice is it really likes doing bolded nouns with colons and then these sort of subpoints. ChatGPT formatted it. I wrote the content. I didn't realize, because I had it generate some templates that I just copied over. It still looks AI generated to me with my words in it. So I was actually not perceiving the content as AI generated. I was perceiving formatting when I saw this, which is kind of strange. I just thought I'd point that out to you because I found it interesting. Pointers and recursion. I think I've talked about this enough. Just about every programming language except the C programming language and now Rust, they do not trust the people writing the programming language to deal with pointers. And the reason for this is all of the security problems we're going to see this term, right? And so, in fact, humans are notoriously bad at dealing with pointers. Kind of doesn't matter because computers have to use them, so you can either, it's like, do you sweep the problem under the rug or not, right? But JavaScript, Java, C#, are, well, except for Java, those are good programming languages, right? And they just don't let you do with pointers, right? I can't stand this because I always want to know what my computer's doing. And I understand that on paper my development time is higher because I have to write pointers myself, and I don't care because also my performance is much better. I attended a very interesting data science talk. Obviously, we're very close with our data science colleagues in this program. And at this talk, one of our speakers was talking about how this data pipeline was, it took a long time to load, like several minutes. That was understandable because it dealt with like a whole gigabyte of data. I was like, I can load a gigabyte in much less than a couple minutes, right? Like that was not a hard thing for me. And one of the like uncomfortable curses of being like a computer scientist that writes low-level languages all the time is you sort of realize how bad all code is, right? Like when this computer got sluggish because it was capturing pixels and throwing them over a pipeline into the internet, right? I was surprised that was sluggish, not because I forgot I was doing screen capture, but because I know exactly how many bits that is and how many operations I can do per second, and it shouldn't have been that slow, right? And I feel the exact same way about the network engineering between this device throwing bits to YouTube Live and how long it takes to show up over here. I know how low my net latency speed is to the Google data center in the Dalles that has to be serving that YouTube, right? I don't know why the latency is more than a quarter of a second. And it is over a quarter of a second because there's things that don't make sense in the pipeline, right? Once you learn about these things, I think it is rewarding to experience them and to understand that like a lot of the frustrations of modern computers can be solved by just writing good code. And it's not like that's easy, right? But we should always keep that in mind when we're deciding what's possible and what isn't. I think a lot of the big results of cloud computing is there were a lot of things that just weren't done because they were hard. And over the space of a couple decades, people just wrote progressively better code, and now it's all possible, right? I have heard two things, right? So I'm teaching the C programming language this term. I'm interested to teach it to all of you, because usually I try and get to students before they get old and set in their ways, which usually happens before you get a master's degree, right? And so, like, sometimes I teach, like, sophomores the C programming language. And they, like, think it's cool because it, like, reminds them of Dark Souls and it seems hard for no reason. And then they, like, get older and they're like, oh, it's actually hard for good reasons that make sense. You might be, like, really, really good at PHP. Right? I don't know. Are there any PHP people in here? Bad example. There's people around that are really good at PHP. And when you start teaching them C, they don't think it's hard. They're like, oh, it's like everything makes sense in this language. It's so straightforward. It's so simple. And to those people, I instead say, well, yes, that's because computers make sense. And they're good and they're easy and they're simple, right? Compared to Python, this might feel like getting a root canal. I don't know. I don't like Python, right? So I've been inoculated against that, right? But some students have a strong negative reaction to C. And I think the thing the strong negative reaction to is that, like, you're used to something being easy, it suddenly becomes hard, and maybe that, like, feels bad for some reason. And then, like, that's understandable, right? Like, if I went to the gym every day, and suddenly instead of being able to, like, lift 45 pounds, I couldn't lift 7 pounds, I would be up in my feels, I'd be crying, I'd be, like, pounding protein calories or whatever it is you do, right? And so, I understand how that can be frustrating. That said, it does make you more powerful. There's an interesting essay on this, and the reason I send all of my students this essay has mostly arisen as a result of being what used to be almost exclusively a Python and R program. And we had a lot of R programmers going around that were talking about how much better the R language was than the Python programming language. And I would ask them why. And they would tell me things that were not true about R and were true about Python. And I got really nervous we were sending those people into job interviews where they're going to be asked to justify their choice of language. It turns out, I think, there's some very principled interest in things like R Markdown being a cool way to express yourselves, and the RStudio IDE being a lot faster to load than VS Code. Those are both true. Neither of those are language features of R, right? And there's also some really cool language features of R that it has, for example, delayed evaluation. So you can call an R function on an expression. The expression will not be evaluated before the function is called. This is possible to do in Python and extremely challenging. You have to use generators to do it, which is not a pleasant way to do things. when I found that out about R, I was like very excited. This is a functional programming technique common to things like Common Lisp, Haskell, Standard ML, these functional languages that academics like me are really into. And it turned out that was not why a lot of people were into R, when it was quite clear to me that that was a cool reason. I do think you're better off arguing that R is really cool because it has delayed evaluation than you are that you like R Markdown documents, because you can write Python in an R Markdown document. And in fact, you can write CUDA C++ in an R Markdown document. And there are very few problems that cannot be solved with CUDA C++. Right? This is a good essay on how I think, not necessarily a good way to think about programming languages, but a defensible way to think about programming languages. So if someone asks you something, you don't say something that makes you look like you aren't familiar with other languages or haven't tried to learn. This is written by someone that wrote an early web startup in the very high-level programming language, Lisp. Basically, in this language, Lisp stands for Lisp Processing, and it doesn't stand for that in a way that makes sense, right? It's L-I-S-P, kind of goofy. Lisp functions are dramatically more powerful than functions in other languages, or they were. If you read through this article, whoever this is, some human, wrote this article and talked about why they didn't use Python. And they say, well, Lisp can generate and process lists in a single line. Lisp contains anonymous functions, such as lambda expressions. Lisp contains this. All of those features are now in Python. So Python is the language now. I'm teaching another unrelated class this term on theoretical computing, and I'm teaching that class in Python because Python now has all of the mathematical expressiveness necessary to be a Lisp-like language, but also you can get a job for knowing Python, right? So Python is the language now. This is no longer a defense of Lisp, it is now a defense of Python. But it is also a defense of thinking critically about the type of language you're writing. I'm going to claim... Yes.
Does Lisp stand for something?
Lisp processing. L-I-S-P, and they just capitalize all of them. It is the second oldest language in the world. It came out in 1960. It was intended for AI. Google it sometime. It's kind of like historically interesting. The early versions of R were written in Lisp, so it's kind of relevant to this program for that reason. And I think it shows up in some other places, but it's a cool language. It's not really practical to use for anything because it doesn't have the tooling support. I do think I was surprised in like 2010 when all of the code in the world was being written in Java for what I perceived as no reason, and now I realize was the Java virtual machine. I am less surprised now that all the code in the world isn't written in Lisp, but it does still seem quite a bit better than JavaScript, which is what everything's being written in, right? So like, there's some of these languages that have been around forever, and it's like hard to know why they're not being used. Lisp is one of them, right? And Fortran is not, right? Like we know what happened to Fortran. It has some good things in it and not others. No one's ever really had a strong argument against why we don't just all write Lisp, right? It just didn't happen. And I think it's maybe because it wasn't owned by Sun Microsystems or something like that, right? This is, Kennedy is actually my legal middle name. And so I think it's reasonable to say that there's times that you can do things because they're hard. I only do crossword puzzles Thursday, Friday, Saturday, Sunday, because I don't find them interesting Monday through Tuesday. Monday through whatever I said. The set complement of what I said. You're all responsible for knowing what I said. I can just make things up. Okay. We can do things in C we can't do in other languages. I will convince you to like C, I promise. When I initially pitched this course to Jamison Watts et al., I was like, look, we have two core limitations. We're not covering any of the sort of security concepts, 100-level topics or AP cybersecurity level stuff, things like the difference between confidentiality, integrity, and availability. That stuff is like not necessary to know, but it's helpful. They're good vocabulary words. And I think oftentimes when they're taught like in high schools, they're not taught rigorously, they're not taught mathematically, and they're not falsifiable. In this class, they are going to be falsifiable. And the way I'm going to falsify them is with systems programming. You're not teaching students about high-performance code. You're not teaching students about executables. You're not extremely comfortable with command line utilities. We're not extremely comfortable with the file system. I'm going to try and solve all of those problems at the same time. Along the way, I realized there's some other low-hanging fruit we can get for free, I think, which is a little bit of modern development. I'm going to ask us to write our code inside containers, and I'm going to ask us to write it using command line text editors. I think these are independently useful things to use, and they make sense to use on C, and they don't make sense to use on Python, because Python really should be written in VS Code or PyCharm. It just should. C shouldn't be written at all, so it doesn't matter how we write it. These learning objectives map exactly to what we're teaching. You can review them or not at your leisure. This sketch did not turn out as well on these slides as I want, so I'm going to show you the same thing somewhere else. This was styled in Mermaid 2 weeks ago before I learned GraphViz, and now I'm styling all of my things differently. And in a few more weeks, I'm going to switch to TIKZ, T-I-K-Z, which is a graphics library in LaTeX. I don't know, I like making diagrams, and maybe you do too. I taught Draw.io a year ago. When I was putting this together, there are, I can't hold up 14 fingers. There's 14 class sessions, right? And 14 divided by 2 is 7. And you can't do anything the first week of class because you have to go over the syllabus. And you burn a minimum of 1 week to a midterm. And if you don't give a midterm, you have no idea if you're teaching or not. So I was unwilling to give those up. That leaves us with 12 weeks of instructional content, right? And then I was thinking, well, I said you should know confidentiality, integrity, and availability. Those are cryptographic goals. And if I spend 2 weeks on each of those things, that gives me 6 weeks. And if I teach those using the SHA and RSA cryptographic algorithms, then it turns out you know all of the technologies you know to implement blockchain, Merkle trees, and therefore Bitcoin at a pace of 1 every 2 weeks. Then you're thinking, hey, I bet these grad students want to really cook in here, right? So you can give them a course final project where they have to implement Ethereum. That's the idea. So after this week, we're going to take 2 weeks on SHA, 2 weeks on RSA. We're going to take a week on AES, and then we're going to do the midterm. We're going to come back. We're going to do blockchain, which is actually easier than Merkle trees, which I didn't know until I went to implement both of them. And I was like, wow, Merkle trees are really hard. And it turns out they're not. I was bad at things. But until you find out the trick, they seem a lot harder than they are. And then you put a Merkle tree, which is a binary tree that is signed by cryptographic algorithms, and therefore it can be embedded in an array, and it's really high performance and raises a lot of interesting questions about, for example, how you can implement a distributed file system. You take that Merkle tree and you put it inside a blockchain, which solves this like really interesting network theory problem of distributed consensus. It's something that's been proven to be impossible, and there are continuous competing algorithms getting closer and closer to offering better guarantees. Super cool stuff. So we're going to put the Merkle tree inside the blockchain. That's the Nakamoto 08 Bitcoin result, and that's your course final. So that's the plan. The midterm cuts right here, right through these. And then this is a offline asynchronous final. I'm going to assess how much I'm going to ask you to do by my assessment of how much I have successfully taught you over the term. So just look for something reasonable. What is SHA? Okay. SHA stands for Secure Hash Algorithm. We work with SHA-2 because the first one is not secure anymore. There is an SHA-3. We don't have to use it because the second one is still secure. It's just ready, right? They got it ready to go if there's a problem. What does SHA do? SHA-2 takes a lot of bits, many bits. It takes something like the size of an operating system or a data lake house that you have stored on BigQuery. Enormous numbers of bits, quintillions, right? And it turns them into a signature that is 256, 512, or some other number of bits long, but everyone uses 256 and 512. Bitcoin uses 256, so that's the version we're going to do in this class. If you're here taking this class from me next year, we're going to be doing it in Rust on 512 to do a different result later. Stick around if you're part-time, we'll have fun, right? And if you don't, you can come back for free, I think. Does Hillary say you can take my classes for free after you graduate?
Oh.
You should ask her about that. If I'm here for life, you should all be, right? You know, that's what I'm saying. Okay, when I was a small child of only about 26 years old, there was this show on the internet called Game of Thrones. And every week, I would go onto a sketchy torrenting site on the dark web, download a link that said it contained Game of Thrones for that week, and I would do this until I successfully found one that was actually Game of Thrones. I usually took 7 or 8 tries. I would finish watching Game of Thrones, and then I would reformat my hard drive, because that was the only way to get the thing secure. So what I was doing there was I was not monitoring data integrity. I was not checking that the things I was downloading and then running with unrestricted access on my computer were Game of Thrones. If I knew what I knew now, I would have installed all that stuff inside Podman, right? But I didn't know about it then because I was young and stupid, right? So the solution to this is what Ubuntu does. It's probably around here somewhere. Yeah, I'll accept everything. We're just talking about integrity. So I think, oh, this is a lot of clicks. Oh, I'm downloading it. Let's stop that. This is a very large file. Whenever you download an operating system, which I do pretty regularly, which I'm not really proud of, you can make sure you got the thing you actually wanted using SHA-256. To look at the file you downloaded, compute this signature over it, and make sure it's what Ubuntu says your signature should be. Because otherwise, someone might have been squirreling around with your bits and doing all kinds of, I don't know, sketchy nonsense, we'll say. Perhaps putting a backdoor in there, or, you know, adding an extra password. So, generally speaking, when you download something off the internet, you should check its SHA-256 hash. Does anyone actually do this? I don't know. I'm not a Linux system administrator, but I'm guessing absolutely no one does that. You're taking a cybersecurity class, so you're going to learn how to do it. Are you actually going to change your behavior in real life? I don't know. It's up to you. It remains to be seen. But you're welcome to do so. RSA is like maybe the coolest mathematical result I've ever seen. There's a bunch of students down in Salem. I like to call it salami. I don't know if any of you have heard that, salami oregano. They took this class called number theory last term, Math 462. And apparently what they did in that class is they all implemented RSA and then they brute force attacked each other, and the person that defeated the most attacks got the highest grade in the class. So people are doing this for fun. What RSA does is I put a numerical value in my Twitter handle. This only works on Twitter. It does not work on X. And then if there's a dissident named, for example, like a name that rhymes with Smedward Odin, that person can send me something that is secure in a way that only I can unencrypt it, and no one else can, but is secured using the bits that I have in my Twitter account. And then, of course, what will happen is the NSA will notice that I'm communicating using a secure technology and then still show up at my house to arrest me, and I'll have to flee to a geopolitical adversary of the United States. Anyways, it's a very complicated system. So this is based on having 2 prime numbers, multiplying them together, and then a bunch of things in modular arithmetic happening. So we avoid having numerical collisions between different arithmetic results, right? It's very cool. It's fun to implement. It is really, really hard to implement in languages like Python that aren't numerically precise, and it is really hard to implement in languages like C that don't handle extremely large numbers very well. There is no easy way to implement this. We're going to implement it in C. I think I have a guest speaker on AES, so I'm not going to talk about it too much, but I know someone that did an honors bachelor's thesis in it, who I'm going to try and get in here. On the midterm, I'm going to ask you to write a little bit of C. I'm going to ask you about confidentiality, which is the thing provided by RSA, integrity, which is the thing provided by SHA, and availability, which is the thing provided by AES. And then we're going to move on to cryptocurrency and the blockchain.
Yeah, so you said what SHA stood for. What about RSA and AES?
I can't remember. So the R and S are Rivest and Shamir, which is 2 people's initials. AES stands for Advanced Encryption Standard. Adelman. It stands for people's names, so knowing what it stands for doesn't help you. AES is Advanced Encryption System. Somewhat helpful once you know the difference between encryption and hashing, and not really helpful until then, right? And I also think names like secure and advanced are like, okay, sure, buddy, right? Like, it's like if computer science were really a science, we'd just call it computer, right? You know, and I kind of feel the same way about the secure hash algorithm. It's like you can just call it the hash algorithm, right? Like if it's secure, we'll find out. I claim RSA plus HHA equals Bitcoin. This is actually not true. I didn't know this when I started developing this course material. Bitcoin has changed to elliptic curve cryptography, which has benefits that are very interesting for reasons that I actually studied while I was working on my doctorate, but I didn't know that at the time. The problem with elliptic curve cryptography is it's not as cool as RSA. So I'm like, we'll just teach RSA in this class. GitHub is still accepting RSA keys, though they request elliptic curve cryptography keys, so I think we get like another 5 years of RSA, and I'm writing it all the way out. I think it's a cool technology.
Can we learn about them a little bit?
A little bit, yeah. I think I'll probably do 1 hours on it. I was interviewing for this position years ago, and I'm a computer scientist, and there were a bunch of software engineers around. I think we've all met software engineers, right? They always say things like, that's fine in theory, but how does it work in practice? Like I have any idea. Like, do I look like I practice things? No, right? Like my idea of practice is like you get your theoretical result published, right? That's like, oh yeah. And so they were like, hey, you can give a guest lecture or a sample lecture on whatever you want. And I was like, cool, linked list. It's a recursive data structure. And they're like, has anyone ever used linked lists like in the last 40 years? And I was like, I don't know. Turns out, yes, blockchain is a linked list. So I'm claiming I was correct the whole time with software engineers. They're trying to trick me with their schemy ways and actually having value to contribute to society and all of that other stuff. So here we are. I've defeated my adversaries. I'm now teaching a class on linked lists. Yes. All right. And then the next thing they said was like, well, what about binary trees? And I was like, that's my second favorite data structure. And they're like, I bet no one actually uses those. And I was like, oh yeah? What about the Merkle tree? A binary tree, not a binary search tree, that is balanced. That is a balanced binary tree. What? That sounds like I'm talking about algorithms. This is crazy, right? These things actually exist in real life? They do. And they embed very well in arrays because balanced trees, you can just load them straight into an array and then use the tree branching to determine the indices, and you realize now that I am talking about pointers, right? So these things, ludicrously cool. We're going to implement a Merkle tree in C because I want to, and you can help. If you put these two things together, I think you get Bitcoin. It looks like it's going to be pretty difficult to be compliant with the modern Bitcoin standard. Bitcoin Core is a lot more lines of code than the old Bitcoin, and the old Bitcoin is written in Microsoft C++, which is like not a development environment that people use anymore. So I don't know that we're actually going to be compatible with actual existing Bitcoin, and I think that's okay, because the version I'm vectoring towards is consistent with the descriptions in the text and is therefore theoretically correct, if not practically correct, and that's what I really care about, right? One of the benefits of this not actually working is you won't actually use any of the code you write, which will be ludicrously insecure and low performance. So never use it. But now you will know how the people that worked on performance engineering this for 15 years started out 15 years ago, which is interesting. Oh, right. This is what you're doing. You are in CS 540, so you have additional responsibilities, which is you have to write a white paper. You have to conduct experiments. And I think many of you know either how ethics or visualization works, so I'll probably request one of those two things in here. Bitcoin is, of course, unethical, so you can talk about that, or you can visualize how well you documented it, right? And then there's a variety of ways to improve Bitcoin, right? So I'll ask you a few things about that. I talked to you a little bit about structure. I think the one thing I didn't say is we do 1 week of enabling technology combined with 1 week of teaching the thing. So next week I'm going to teach you about the C programming language before teaching you about SHA, and then we'll have labs that I just pick, I think, the hardest relevant piece of content every week and do a lab on that. I think that's that. Okay. We're going to introduce the technologies quickly before we go into the lab section. Do you want to break now, and then I can run through this bit of lecture, and then we can go into the lab? Yeah, let's do that. You usually break for half hour? Cool. See you in a half hour. I'll start a timer for me. I won't be strict.